So we spent the first couple weeks looking at kinematics tables, handling velocity and accelerations. Now that we're dealing with writing equations of motion using Lagrangian dynamics, I really only need part of the table. So what is that? I need this, and the three of these. So looking at the table, as in the past, these still add up to the velocity of p. It doesn't mean that the accelerations are zero. I just don't need them. So this I'm not concerned about. So what do we have? Okay, we're using the inertial frame right now, so we still have I and J. How many degrees of freedom do we have? The cart can move left and right, and the bar BP can spin. So we have 2 degrees of freedom. So our Q, which is our generalized coordinates, would be x and theta. And we know for kinetic energy, we'll ultimately need to know the velocity of each of these masses. So what do we have? Inertial, so the omega b, as we see, we had all zeros. Inertial frame. Our displacement vector, as in the past, has a component r cosine theta plus the r sine theta term, and that we've done a bunch of times here. The car we say can move left and right. Its velocity, as in the past, for this b is just x dot, right? Those are the only ones we said we're concerned about, right? The ones with the check marks we were concerned about for velocities and accelerations. Right now, we're only looking at velocities. So I need this part of the worksheet, this part of the worksheet, and this I have to think about. The rest is just mindless math. So what is the derivative of r cosine theta, where r is constant? We're going to have r, we're going to have sine theta negative, and because we need to mix in the chain rule, because the derivative with respect to theta is minus sine theta, but then d theta dt, as we've done many times, gives us a theta dot. Here, similarly, it's going to be r theta dot cosine theta, 0. We have no omega line until we get to body fixed, so 0, 0, 0. So in a moment, we're going to take and use this information. So I've transferred the velocity at point P from my kinematics table to this new page with the drawing. We have 2 degrees of freedom. Again, Q equals x and theta. We said we write all of our velocities at the center of gravity. So the center of gravity for this mass of the cart, I'm going to call M1. For this bar that rotates, I'll call it M2. G is the location of its center of mass. So the velocity at G, I can either take out another kinematics table or recognize that if I assume, let's say, that G is at halfway, it would be minus r over 2 theta dot sine theta I plus r over 2 theta dot cosine theta j. VB is simply x dot I. And again, we've done that many times in class. All right, so we want to create equations of motion. We have this thing called Lagrangian, which is L, which is equal to capital T, which is kinetic energy, minus capital V, I'll draw like that, which is our potential energy. We said we're focusing on 2 pieces. The kinetic energy has a translational part plus a rotational part. So let's take a look at that. The translational part I'll just abbreviate here, is 1/2 the first mass, and that's the mass of the cart, m1, times its velocity squared, x dot squared, or vb dotted with vb, plus the bar is 1/2 its mass, m2, times vg dotted, fix it up a little bit, vg dotted, still not working, dotted, sorry, at the end of the page here, not responding. Still not responding, dotted with VG. I'll try to fix that for the next one. Then we have a rotational component, T rotational, and in this case, it's just going to be 1/2 the mass moment of inertia at the center of gravity, IG, theta dot squared. Okay, I'm going to pause it for a moment, clear the screen, and work on the potential energy point.